In many modern machine learning problems, for instance deep learning, the model is highly overparametrized, meaning that there are many possible parameters for which the training loss is zero. This can arise when the number of parameters is larger than the number of training instances, which is frequently the case for deep learning models. Nevertheless, these overparameterized models are empirically observed to generalize quite well, and this unexpected generalization may be explained by a training algorithm such as gradient descent somehow inducing implicit regularization of the model. For example, prior work has shown that very complex nonlinear models nevertheless may behave in some circumstances like kernel methods with corresponding RKHS regularization. In the original presentation, it was argued that the width of the model going to infinity was what induced this kernel-like behavior. More recently, Shizan-Bach argued that instead, initializing with parameters of large magnitude actually controls entrance into this regime. Now, in contrast to this work on the kernel regime, other work has shown that under different conditions, some models can exhibit very different non-Hilbert norm implicit regularization. This does not correspond to any kernel and therefore cannot be explained by the previous view. This raises the question of what implicit regularization might explain the empirical performance of complex overparametrized models like deep learning. How does the implicit regularization depend on factors such as the scale of the initialization? Towards understanding this question, we studied D-Homogeneous models trained to minimize the squared loss using gradient flow, which is equivalent to gradient descent in the limit as the step size is taken to zero. Following Shizan-Bach, we identified the scale of the initialization as a key determiner of the implicit regularization when training certain homogeneous models. We capture the scale of the initialization through a parameter alpha, which ranges from 0 to infinity. We initialize at alpha times some fixed vector, w naught, and see how the solution reached by gradient flow depends on alpha. Shizan-Bach showed that generally, taking alpha to infinity leads to the kernel regime and the associated RKHS implicit bias. We will show that for certain models, the limit as alpha is taken to 0 instead yields rich implicit biases which cannot be captured by any kernel. However, the more interesting case lies between these, where the scale of the initialization is neither 0 nor infinite, since this is where machine learning models are actually trained. For several simple models, we're able to precisely characterize the implicit bias as determined by any finite value of alpha. We start by considering a simple two-homogeneous model. This is just a linear model, albeit with this non-standard squared parameterization. This can also be viewed as a two-layer diagonal linear neural network, as pictured on the right. We use two sets of weights, W plus and W minus, which A allows us to represent all signed linear predictors using this parameterization, and B allows us to initialize so that the corresponding linear predictor is 0, without this being a saddle point from which optimization would never escape. Now, this is a pretty simple model, but it already exhibits interesting implicit regularization, which changes as a function of the initialization. For this model, we define beta alpha infinity to be the linear predictor that results from training after initializing both W plus and W minus to be alpha. It was already known that the kernel regime for this model corresponds to implicit L2 regularization, and that beta alpha infinity would therefore approach the minimum L2 norm solution with 0 error as alpha is taken to infinity. We also already knew from Gunasekar et al. 2017 that when alpha goes to 0, the rich regime corresponds to implicit L1 regularization. So beta alpha infinity will approach the minimum L1 norm 0 error predictor when alpha is taken to 0. But what happens for finite alpha in between? We provide a precise analytic characterization of the implicit bias as a function of alpha, which is captured by a regularizer we denote Q alpha. It's probably not obvious to you why this should be the bias, or even how we came up with this strange-looking regularizer. In our paper, we produce a method for deriving the implicit bias as the solution to a particular differential equation. This allowed us to solve for the implicit regularizer without having to guess a bit beforehand and without needing to resort to something like guessing and checking. Despite its strange appearance, Q alpha, as determined by little q, has a somewhat natural interpretation. Near the origin, little q is very nearly quadratic, and far from the origin, little q is very nearly linear. Therefore, for any particular beta, when alpha is large, beta over alpha squared will be very small, so the action will be around the origin, and thus the regularizer will behave like the L2 norm. On the other hand, for small alpha, beta over alpha squared will be very large, so the near linearity of little q far from the origin will govern the implicit regularization, and thus this will all behave like the L1 norm. And of course, for intermediate alpha, the regularizer will somehow interpolate between L1 and L2 regularization in a way that depends on alpha and also the problem at hand. To see how this implicit regularization might play out, consider a sparse regression problem where the optimal linear predictor on RD is S sparse. In this case, L2 implicit bias is not very helpful, and omega of dimension samples are needed in order to generalize at all. On the other hand, L1 implicit bias is very effective, and only S log D samples are required for generalization. When we conduct an experiment for this sparse regression problem, we see that alpha therefore plays a very big role in the generalization. On the left panel, we see that using a small initialization alpha is really important to achieve low test error. And in the right panel, we see that this is driven by the implicit bias. When small alpha is used for initialization, this leads to a predictor with only slightly higher L1 norm than the minimum L1 norm solution, and this gives us generalization. On the other hand, larger alpha leads to approximately the minimum L2 norm solution, which does not generalize at all with the number of samples that were available. Another way of looking at the same problem is, for a given sample size n, how small do we need to make alpha in order to obtain a small test error? The dashed vertical line here indicates the number of samples needed for the minimum L1 norm solution to reach that test error. We see here that when the number of samples approaches the dashed line, alpha must become exceedingly small in order to attain the same generalization as the minimum L1 norm predictor. And this is because alpha must be chosen very, very small for Q alpha to be a very close approximator of the L1 norm. On the other hand, with only slightly more samples, a much more moderate alpha suffices. We saw in this sparse regression example that in order to attain sufficiently L1-like implicit bias to generalize, we needed to choose small scales of initialization alpha. But it is important to note that if we set alpha all the way to 0, then the model would be initialized directly upon a saddle point, and optimization would never escape, so we would never reach a zero-error solution in the first place. Similarly, as we take alpha closer and closer to 0, we are initializing closer and closer to a saddle point, which presumably makes optimization much more difficult and slower. This suggests a trade-off between generalization and optimization, at least in this case, and it implies that we likely want to operate right on the edge of the rich regime for optimal performance. That is, we would like to use the largest alpha for which we can still generalize. We also study an extension of the two-homogeneous model from before, which is now D-homogeneous. This is analogous in many ways to a deeper model, specifically a depth D diagonal linear neural network. When this model is trained with gradient flow on the squared loss, we can also characterize the implicit bias for any scale of initialization alpha. This time, we can't obtain quite as clean of an expression for the regularizer, but what I've shown you here does fully describe the implicit bias, and as in the D equals 2 case, it closely resembles the L1 norm for small alpha, and it resembles the L2 norm for large alpha. The main difference is in how it transitions between the two. On the left, we show the QD function for various Ds. For every homogeneity or depth D, the models are roughly quadratic around 0. However, as the depth increases, the regularizer transitions from nearly linear to nearly linear much more quickly. Therefore, significantly larger initializations alpha will suffice for L1-like implicit bias when D is larger. Returning again to the same sparse regression example as before, we see on the right that indeed, for any given number of samples n, a much larger alpha suffices to reach small test error when the depth is increased. And this difference is particularly marked when comparing D equals 2 and D greater than 2 as we approach the critical number of samples. Here, alpha can be taken to be many, many orders of magnitude larger for d greater than 2 than for d equals 2. Moving along, we also studied matrix factorization models and found an interesting interplay between the scale of initialization, the width of the factorization, and the implicit bias. To begin, we consider a standard asymmetric matrix factorization model, UV transpose, with U and V both being in Rd by K. Thus, K, the inner dimension, is in some sense the width of the model. However, we observe that this asymmetric factorization is precisely equivalent to a symmetric matrix factorization, WW transpose, with W in R2D by K. These factorizations are essentially the same when we focus on the top right corner of WW transpose. However, we argue that the symmetric factorization better captures what's actually going on. Specifically, consider optimizing the symmetrized factorization after initializing the entries of W to be IID Gaussian with variance alpha squared over square root of K. This results in the off-diagonal entries of WW transpose, which includes the actual predictor of interest, UV transpose, having scale approximately alpha squared. On the other hand, the diagonal elements of WW transpose will have the much larger scale alpha squared times square root of K. So, which of these scales actually controls the implicit bias? Well, it turns out that the scale of WW transpose, the symmetrized matrix, is all that matters. We show, following Shizan-Bach, that when alpha squared square root of K, the scale of WW transpose, goes to infinity, we enter the kernel regime. But importantly, this can happen even when alpha squared is fixed, or even when it goes to 0. So the scale of UV transpose, the actual predictor of interest itself, can actually go to 0 while it still behaves like a kernel method. Therefore, in this sense, the width of the model, K, can play an important role in the implicit bias above and beyond the scale of the initialization. Of course, in some sense, the width was only important insofar as it affected the scale of the symmetrized problem. But nevertheless, when focusing just on the asymmetric problem, as most people typically think of it, it seems safe to say that the width is indeed relevant for the implicit bias. Finally, in the special case of commutative or diagonal measurements, we show that for finite alpha squared square root of K, the implicit regularization corresponds to something like Schatten Q mu norm regularization, but whether this holds in general is somewhat unclear. Now, I'll conclude by mentioning that we also performed experiments with nonlinear ReLU networks, which demonstrated sort of qualitatively similar behavior. In particular, we observed that when alpha is taken to be smaller, generalization performance generally improves. And this seems to suggest that using a small initialization may also be introducing some sort of useful implicit regularization, even for these more complicated and realistic models. Thank you for watching.